at its history and development. So our learning intentions are to explore the history of elements, referring to the Greeks, Boyle, Davy and Moseley. We're going to understand the periodic table as a list of elements arranged to demonstrate trends in physical and chemical properties, referring to Dobereiner, Newlands, Moseley and Mendeleev. We're going to compare Mendeleev's periodic table with the modern periodic table we have today, and we're going to calculate the approximate relative atomic mass of chlorine. So to begin, let's take a look at the Greeks' periodic table. Before the periodic table was ever really discussed by scientists, Greeks believed that there was 4 simple substances that made up the Earth, and these were fire, air, water, and the Earth itself. So Robert Boyle is the first scientist that we're going to look at, and he was the one that gave the first accurate definition of an element, and he's an Irish scientist. And he said that an element is a substance that cannot be broken down into simpler substances by chemical means, and that is the definition from the Junior Cert. Boyle also predicted that certain elements could be combined together to form compounds. Humphrey Davy is next, and he used electrolysis to break down water into hydrogen and oxygen, which led to him discovering the elements potassium and sodium. And by 1800, 25 elements had been discovered. So there was a lot of scientists involved in looking for patterns in the periodic table, and the first one that we're going to look at is Dobereiner, and he is a German scientist, and he spotted trends and similarities among several groups of elements when he put them into threes. He noticed that calcium, strontium and barium had similar chemical properties, and he also noted that the atomic weight of strontium was about halfway between calcium and barium, and he called this a triad. So this is your definition for a triad, and it's very important to know. A triad is a group of 3 elements with similar chemical properties in which the atomic weight of the middle element is approximately equal to the average of the other 2 elements of the triad. So an example here would be chlorine, which has an atomic weight of 35.5, bromine, which has an atomic weight of 80, and iodine, which has an atomic weight of 127. If you get the average of the chlorine and the iodine, you'll get a figure of 81, and bromine has an atomic mass of 80. Unfortunately, that was one of the only triads that Dobereiner found, so more work was needed on the trends. By 1864, there were 60 elements that had been discovered, and a new scientist called John Newlands listed all the known elements so far in order of increasing atomic weight. From this, he noticed a regular pattern. He found that every 8th element had similar properties to the first one. So basically, that the properties repeated every 8th element. From this, he came up with his law of octaves. And the definition is that the arrangement of electrons in which the first and the 8th element, counting from a particular element, have similar properties. However, what Newlands didn't realise was that some elements had yet to be discovered, so problems emerged with his theory as well. So for example, oxygen and sulphur were in the same group as iron, yet they had no resemblance. So Newlands' idea of arranging the elements in order and looking for patterns was correct. To try and form a table, he was basically correct. And that led to possibilities for other scientists to discover new things, specifically Mendeleev, who we're going to talk about next. So Mendeleev considered a table in which elements were arranged in horizontal rows called periods. And he came up with periodic law that we have here at the top. And periodic law states that if elements were listed in increasing atomic weight, the properties of the elements repeated at regular intervals. So these elements with similar properties were in vertical columns called groups. And in some cases, he needed to reverse the order of some elements to make them fit into correct groups. And he left gaps for new ones. So this is unlike Newlands. Mendeleev left the gaps and changed things around a little bit to fit his periodic law. So with groups on the periodic table, elements within a group share common properties. The groups are elements which have the same outer electron configuration. So that means that they have the same number of electrons in their outer shell. And these outer electrons are called valence electrons, and because they have the same number of valence electrons, elements in the same group share similar chemical properties due to their valence electrons. The Roman numerals listed above each group are the usual number of valence electrons. Roman numeral 5 has 5 valence electrons, meaning there's 5 electrons on the outer shell of all elements in group 5. So Mendeleev did reverse some of the elements, but he didn't really understand why. And this wasn't really understood until a scientist called Moseley came along. And Moseley discovered a method to determine the number of protons in the nucleus of the atom, because he studied frequencies of X-rays emitted by atoms and found that there was varied frequencies for the positive charges, which is the protons. So from this, we were able to discover the atomic number. So your definition is here. The atomic number is the number of protons in the nucleus of the atom. And in the modern periodic table that we have today, the elements are arranged in order of increasing atomic number. So modern periodic table law, it's another definition down at the bottom here. It says when elements are arranged in order of increasing atomic number, the properties of the elements recur periodically. So basically, Mendeleev got as far as ordering the elements according to atomic weight, but then Moseley came along with the modern periodic table and they were ordered in increasing atomic number. So this slide here is really important. This is your difference between the Mendeleev and the modern periodic table, and this comes up quite often as it summarizes everything that we've kind of done so far. So in Mendeleev's periodic table, elements were arranged in order of increasing atomic weight or atomic mass, where in the modern periodic table they're in increasing atomic number. There was only 60 elements in Mendeleev's periodic table, but there's 100 in the modern periodic table. Mendeleev's periodic table contained gaps because he knew better than Newlands and decided to leave gaps, but there's no gaps in the modern periodic table. And in Mendeleev's periodic table, transition elements were not put in a separate block, but transition metals in the modern periodic table, the lanthanoids and the actinoids, are in a separate block that you will often see at the bottom of a periodic table. So along with the atomic number, the mass number is also useful in the periodic table. So the mass number is the sum of the number of protons and the number of neutrons. And this is dealt with in the videos that I've done on the atom. So the mass number is always the bigger number, and the atomic number will always be the smaller number. So the atomic number just shows the number of protons, but the mass number shows the number of protons and neutrons. So here's an example of where we can put this knowledge to use. How many neutrons and electrons are in the ion of scandium 3+? So as you can see here in the question, the mass number and the atomic number are given to you. So if we look to see the number of neutrons, the number of neutrons is the mass number minus the atomic number. So the number of neutrons is 45, take away your 21, so that leaves us with 24 neutrons. Now, if we look at the electrons, the number of electrons in the neutral atom is equal to the number of protons, because the number of positive charges in an atom must equal the number of negative charges in a neutral atom. So that's really important for a neutral atom. However, you can see we don't have a neutral atom here. If it was a neutral atom, we'd simply be able to say that the number of electrons is 21. However, that's not the case here. We have a 3+ charge on our scandium, so since the atom has lost 3 electrons, because the ion is 3+, and we know that if you lose electrons, you get a positive charge on your ion, that means that the number of electrons that is actually present is 18, because you do the atomic number, take away whatever the positive charge is on your atom. So isotopes are also very important in the periodic table, and this is a definition that you need to know. So isotopes are atoms of the same element which have the same atomic number but have different mass numbers, and this is due to the different number of neutrons present in the nucleus of the atom. So it was discovered that the percentage of each isotope present in an atom could actually be measured, so that's what we're going to do on the next slide. So this is a sample question, and it does come up usually in question 4 of the exam paper. So a sample of chlorine is found to consist of 75% 3517 chlorine and 25% 3717 chlorine. Calculate the average mass of an atom of chlorine. So the first thing is you always, for these questions, look at 100 atoms of whatever element it is. And the main reason you do that is because they give you percentages in the question. So in this one, they've given you 75 and they've given you 25. And percentage will always match to 100. So always look for 100 atoms. Next, what you do is 75 atoms of mass 35. So there was 75%, or 75 atoms out of 100 that had a mass of 35 chlorine. So that's where we've gotten the 75 by the 35 from. And then you do the same thing for the 25%. There's 25 atoms, so from the 25%, with a mass of 37. So the 25 by 37 gives you 924. And when you put those together, we find that the total mass of 100 atoms would be 3,500, is 35.5. So the last thing we want to look at is relative atomic mass, and this is a definition that comes up quite frequently, and it needs to be known word for word. So the definition is the average of the mass numbers of the isotopes of the element as they occur naturally, taking into account their abundances and expressing them on a scale in which the atoms of the carbon-12 isotope have a mass of exactly 12 units. Now, that's a very long definition, but it does need to be learned off. And then you have the formula underneath here. The formula puts this definition just into more mathematical terms, so it will be important to know that as well. That's it for this video. Read over the learning intentions to make sure you understand everything we've gone through.